This is problem 1 from section 5.3, where it says write the equation of the line 3x1 plus x2 is equal to 5 in a parametric vector form. Okay, so here I sketched the line L. Let's call that line L. How did I do that? Well, I took 2 points. Let's say the point when x1 is 1 and x2 is 2, so 1 and 2, and the other one, let's say the x2 intercept or the y-intercept, when x1 is 0, then x2 is going to be 5, so this point here is 0 and 5, right? So if I have 2 points, I can just connect them with a straight line, and I get the line. Okay, so this question, there are many ways how to solve this question, how to express this line in a parametric vector form. One way, how to call this? First way, how to do this is just to put this in a matrix, right? So it's 3, 1, 5. Obviously here I'll have one free variable x1 and x2. If you take that x2 is a free variable, if x2 is equal to t, then 3x1 plus t is equal to 5. Express how much is x1. x1 is going to be equal to 5 over 3 minus 1 over 3 times t. And from here, the parametric vector form of the line is going to be x1, x2 is equal to 5 over 3 minus 1 over 3t, and x2 is just the parameter t, so this is going to be 5 over 3 and 0 plus t negative 1/3 1. And there's one way how to do this. Well, somebody might ask the question, well, if that's the case, can I just take x1 to be my parameter? Well, of course you can. If you take that x1 is your t, okay, and you express x2 in terms of t, then x2 is going to be 5 minus 3x1, which in terms of our parameter becomes 5 minus 3t. In this case, the parametric vector form just becomes t and 5 minus 3t, which is what? Here you have the point 0, 5 plus t 1 and negative 3. Now here you have to be able to realize that both of these equations are equations of the same line L. Okay, what is important is important that this point 5 over 3 and 0 satisfies this equation, which means it's a point on the equation, right? 5 over 3 times 3 is 5, plus 0 is 5, and 0 and 5, 3 times 0 is 0, plus 5 is equal to 5. So both of these points belong here. And another thing that you have to realize is that these vectors here are scalar multiples of each other, so that means that they are parallel. Okay, they're not the same vectors, but they're parallel vectors. So basically, the parametric vector form asks you to find a point on the line. We agree that this point belongs to the line, plus t times a vector parallel to the line. And why these two equations give you the same line? Because this point also belongs to the line, and this vector is parallel to this vector. Okay, so maybe to some of you this solution was not represented in the solutions of the problem in the book, but you can have many different answers to this problem. And another way that you can do this is just by writing by writing xy is equal to a point plus t times a vector parallel to the line. Okay, so you can find a point just by looking by observation here. Let's say x1 is 1, 3 times 1 is 3, plus 2 is 5, plus t. And now how to find a vector parallel to the line? Well, this equation here gives me the normal vector, and the normal vector is orthogonal to the line. So this green vector here, which is 1, 2, 3, and 1, obviously is orthogonal to the line. Now in R2, it's very easy to find a vector orthogonal to a given vector. All you have to do is flip these entries and multiply only one of the entries by -1. Okay? So a vector parallel to the line is going to be a vector orthogonal to the normal vector. Okay, so this is n. And you can just say, okay, then v is going to be equal to, you're going to flip these entries 1 and 3, and you're going to multiply just one of them by -1. You can see that the dot product between n and v is going to be 0, which means that these are orthogonal. So you can just take this -1 and 3. And this also is the equation of the same line L. Somebody might say, well, what about the vector w, which is 1 and -3? That is also orthogonal to n, right? These are parallel because they're constant multiples of each other. So as you can see, all of these answers are correct answers to the given question. Now, we will continue and cover problem number 2 in the same video that says, given a line in a parametric vector form, find the normal form of this line. Okay, now what are we given? Now I'm given a point on the line, let's call it A, with coordinates 2 and 1, and vector v that it's parallel to the line, and the vector v is 3 and -1. In order to write the equation of this line in a normal form, the definition is the normal vector dot product x minus x naught times y minus y naught is equal to 0, right? Where x naught y naught is the point where n is the normal vector and x naught y naught is the point on the line. So this x naught y naught, it is given right here, and all we have to do is figure out what is n. So if this is our line here, okay, we're given a vector parallel to this line, so that's the vector v. The question is, how are we going to find the vector n that is orthogonal to v, the normal vector of the line? Well, again, the fact that we are in R2 makes it extremely easy for us to find n. All you have to do is flip these entries and multiply just one of them by -1. So there you go. Let's say that I'm going to multiply the x1 entry by -1. So the normal vector is 1 and 3. You can always do the dot product. For in R2 it's very simple. 3 times 1 is 3, -1 times 3 is -3, 3 minus 3 is 0, so the dot product between these two vectors is 0, which means that they're orthogonal. And there you go, you have the vector 1 and 3, dot product x minus x naught, which is 2, y minus y naught, which is 1, and this is equal to 0. Evaluate this dot product. 1 times x minus 2 is x minus 2, plus 3 times y minus 1 is equal to 0. And that's x plus 3y is equal to -2 minus 3 is 5.